Okay, so just to get started, today we have Dr. Freda Shi, who's going to be presenting to us today. Freda is an assistant professor at the University of Waterloo and a faculty member here at Vector, and she also holds a Canada CIFA AI chair. She's recognized as an expert in linguistics and AI, and her work explores the intersection of NLP and cognitive science, with a focus on how linguistic structures influence AI's ability to understand and reason. So without further ado, please join me in welcoming Dr. Freda Shi.
Thanks for the kind introduction. All right, so this talk, we'll be talking about some basic interaction between linguistics and computer science, and how I will be showing basically how linguistic insights will be deepening our understanding of AI systems and currently generative AI systems from the cases of reference frames or frame of reference and logical reasoning. So I'd like to start. I'd like to start my talk by a quick review of the historical interaction between linguistics and computer science. So the time axis is around this. Just basically around the 1950s to 1960s, the famous Chomsky hierarchy is basically proposed and influenced a lot of areas in computer science as well, including programming language and also formal language processing. And almost around the same time, the Georgetown IBM experiment has proposed. Basically, they released the first ever promising machine translation system, translating Russian to English. This kind of system could be viewed as a little bit simple from today's view. So what they are doing is basically just mapping these Romanized Russian characters or words into indices and using rule-based machine translation methods to match into English words. And again, using rule-based methods to filter out some English words to make sure the language in English just looks pretty good to most native speakers. And actually, the time moves after about 30 years. Around the 1990s, Jeffrey Ellman actually proposed recurrent neural network. Jeffrey Ellman is a linguist, he's a psycholinguist, and he was drawing inspirations from the fact that humans processing words time by time, and we are predicting the words from time by time, and proposed the architecture of recurrent neural networks that influenced AI by a lot. And until 2010s or until 2018s, the architecture of recurrent neural network was still pretty much influential in NLP tasks. And now, actually, starting from 1990s, another 30 years passed. So nowadays, transformers proposed by all these leading industrial labs are kind of dominant in terms of the natural language processing architecture and all the generative AI backbones. And now is a good time to review. So whether linguistic insights are still helpful or not. So basically, the transformer architecture does not include any explicit linguistic inductive bias in that. It's basically every token could be attending every token else. And then under this framework of machine learning schema, are linguistic insights still helpful? So actually, the question I'm asking here in this talk is a converse of a popular question that recently asked mostly by linguists. So they asked the question like whether language models could benefit the development of linguistics. And fortunately, the answer is fairly optimistic. So recently, linguists find that language models could be used to help generating hypotheses for linguistics. What they are doing is to pretend the language models is having some similar behavioral pattern as humans and use the language models as the proxy for testing some initial pilot hypothesis. And once we find some positive evidences from these pilot experiments, then we continue on testing on real human data. So Misra and Kim recently just released a preprint supporting this experimental protocol, which is pretty much exciting in terms of development of linguistics, especially psycholinguistics. And in a more broad view, Futrell and Mahawat recently just released another piece of preprint showing that language models can benefit the development of linguistic theories from various perspectives. And actually in this talk, I'm kind of taking the opposite perspective. Like I'm asking the question, what tasks are hard for the current large language models and vision language models? And I'm drawing insights from linguistic theories. So basically, our work is benefiting from very kind of conventional linguistic theories. One of them is frame of reference theory that is well summarized in Levinson 2003 in his book. It's kind of, there are a kind of much longer history of frame of reference theory development before that. And we use these kind of theoretical framework to identify the reasons for spatial reasoning issues in vision language models and analyze what's going on within the vision language models. And in another line of work, we leverage the insights from possible world semantics and modal logic to explain text-only language model behaviors. So these analyses actually can also offer the insights on what we should do to improve the language models and what kind of current drawbacks are important. All right, let's just come into the first part of this talk, how we use frame of reference theory to analyze the vision language models. Before delving into the details of this exact work, I'd like to start by reviewing some common types of vision language models to give you a background. So one of the common types of vision language models is image text mapping models. For example, CLIP serves as a pretty good representative. And actually, this type of model is not, CLIP is not the newest one, or it's not the first one to propose this kind of model. Here, Jamie Kirrell's here also at Toronto, as far as I know, is the kind of the first one proposing using these kind of image text models to learn some meaningful representations in the middle that encodes both semantic information from image and text. So the key idea here is what you do is basically encode a bunch of text into vector space, and you do the same thing, encode a bunch of images into the same space, and you quantify the similarity between the image and text by the whatever similarity metric you compute within this joint embedding space. So for example, under the CLIP framework, the similarity metrics could be like pretty naturally probability after the softmax, where you take all the row values into the softmax operator or all the column values into the softmax operator to predict a probability distribution. And this probability just serves as a natural quantification of the endorsement level. So by the endorsement level, I'm just saying you can just understand it as how the model thinks this pair of image and text maps with each other. And another common type of vision language model is, I call it conditional generative models. It's kind of not a canonical name. So basically what the idea is, you encode the image and text into the same embedding space, which serves as the input of the transformer language model here. And you generate basically text, and technically you can also generate image from this setup. You generate text one token by one token as the response conditioned on both of the image and the text. So here is automatically also a probabilistic model, and the probability of generating the next token, or basically also can kind of serving as a quantification of endorsement level. So if you just say, if you have a question to the vision language model and the corresponding images and the probability of generating some affirmative answer, for example, yes, comparing to the probability to no, that will be kind of a quantifier of how the language model thinks these pair of image and text match with each other. All right, so the task again in this work we focus on is spatial reasoning in vision language models. So this issue is first raised by Hongyu Liu et al. And they say state-of-the-art vision language models just fail in spatial reasoning, even if the spatial reasoning task itself is quite simple. So it's just recognizing the spatial relations on the top of, below, and to the left of, to the right of. So the evaluation they adopted is mostly comparing the endorsement level for the ground truth captions versus the distractors. So they expect for this image, input this cat image and the true caption, the cat is in front of the potted plant. Actually, the potted plant is here. This is not a super good example because the potted plant is not that salient in the image. And their task requirement is to expect this caption receiving a higher endorsement level than the caption below. The cat is to the left of the potted plant from any perspective. This is never true. And similarly, the spatial reasoning could be kind of not limited in left, right, in front of, or to the back of. These kind of basic relations. They can be also vague. The pizza is at the edge of the dining table, and versus the distractor caption, the pizza is behind the dining table, it definitely should be receiving a higher endorsement score. So this source of complexity, or why vision language model generally fail in these kind of seemingly simple spatial reasoning tasks, could be they made this conjecture that spatial relations are subjective and are not always clear defined. So here I just wanted to elaborate a little bit more on why we are interested in the endorsement level as the evaluation metric. So an alternative way, so you can imagine like an alternative way is to evaluate the generative models in terms of the exact matching-based accuracy. So whether it generates yes for some yes/no binary question, you think this answer is absolutely correct and receive an accuracy of 1, otherwise your model receives an accuracy of 0. So this comes with 2 major issues. Actually, some language models, pretty many language models, according to a recent investigation by Gentella et al., supports that language models tend to answer yes to binary yes or no questions. So no matter what your question is, they are having a strong bias towards answering yes. And maybe this is because of the RLHF or alignment kind of things, and the language models just tend to not decline the user's request by first answering a yes and then the more detailed questions. And another issue here is exact match-based accuracy does not consider the competence of models. So here I'm slightly abused the word of linguistic competence to justify the intuition. So if we just look at this simple toy example. So here, with the ground truth answer no, case 1 is clearly better than case 2 in terms of the endorsement level. Because case 1 is just putting 90% probability to the ground truth answer no, where case 2 is just put a slightly marginally higher probability to the ground truth answer. Although if we set a threshold to be 50%, both case 1 and 2 will be considered as correct. So having this endorsement level just enables some nuanced analysis in terms of how confident the models are. And actually, from another perspective, most of the generative models have a solid probability foundation. So it is pretty natural to use probability-based metrics to quantify the model's competence. Okay, so this is the kind of task we are interested in. So frame of reference, I just wanted to give you an example to show the complicatedness of the task. And basically, frame of reference just offers this line of theory offers a taxonomy of the analysis of part of the spatial reasoning tasks. So let me just do a quick survey. So for each of the following captions for this image, do you think it's a good description of the image or not? If you think it is, please raise your hand. So let's look at the first one. The tray is behind the car. How many of you think it's good? Yes, including me. All right, so this is mostly endorsed by people. Next, so actually this is basically from a reflection relative frame, which I will be explaining later. And next, the tray is in front of the car. How many of you think this is good? None of you? All right, actually, this is good to me. So maybe because I'm kind of, I am a Chinese native speaker, which I will be elaborating later. And recently, some recent research just has said Chinese, German, and Japanese native speakers are more kind of tending to agree with this caption more than English native speakers. All right, and this is actually, if you endorse this caption is correct, then you are actually from the translation relative frame. And next, the tray is to the right of the car. How many of you think this is okay? Yeah, some of you, so including myself. So actually, if you put yourself into the car's perspective, the tray is indeed to the right of the car. So this is called ground intrinsic frame. So if you just view in this caption, the ground is the car and the figure is the tray. If you use the car's intrinsic frame, that is exactly this caption. So actually the difference between reflection relative frame versus translation relative frame is basically the difference like this. So by translation relative frame is I'm imagining I am a robot sitting in this picture. Like I am facing the car and the tray like this. And if I'm facing the car and the tray, so the car is in front of me, the tray is further in front of the car, and that's why I can endorse the caption, the tray is in front of the car. And actually, from the reflection relative frame, what you are doing is imagining you are facing the car, and then your reference frame is being reflected with the axis of the screen. So that is how the name is coming from. So our natural question regarding vision language models or these kind of generative models is, do vision language models also endorse these three descriptions, and to what extent? So in this recent work, it's just get accepted by ICLR, and mostly led by Julian Zhang and Zicheng Ma, whose picture is hidden on the top right of the screen. And we generate a synthetic data set that enables the analysis of frame of reference knowledge in vision language models. So actually, we also complicate the scenario by adding another addressee. So here is a woman here with some specific pose to show her the intrinsic frame of this woman is clearly this direction. It's clearly just that the woman is facing the car. So actually we ask three types of questions. From the camera's perspective or from camera's viewpoint, is the basketball to the right of the car? So it's basically this scenario, and the answer should be yes. The ground truth answer should be yes. And from the addressee's perspective, that is to say, from the woman's viewpoint, is the basketball to the right of the car? And in this case, yes. And another question is from the ground object's perspective, is from the car's perspective, is the basketball to the right of the car? And in this case, we should be answering yes. And actually, for all the questions without the color match, we should be really answering no. And the evaluation metric here is the soft accuracy. So it's basically the normalized ground truth probability. We just investigate whether how much probability mass the model is assigning to the tokens, yes and no, and normalize the probability correspondingly. And we use this normalized ground truth probability or soft accuracy to quantify how much the model is kind of holding the confidence in terms of recognizing the correct answer for each scenario. And a few other metrics, mostly for cross-validation purposes, can be found in the paper as well. So here comes the main results. So 0.5 is basically the random guess baseline. You basically just assign the same probability to yes and no, and you will be getting this random guess baseline. And we evaluate 6 state-of-the-art model. I'm not sure if all of them can be considered as state-of-the-art by today, but at that time we conducted the research, all of them are state-of-the-art. But actually, the result is only some of the models give non-trivial accuracies only from the camera's perspective, which is the most canonical perspective that most people agree with. So actually, these models are all struggling with the perspective taking, like putting their shoes into the woman's, like the addressees, or the putting their shoes into the ground objects. Okay, so since it's giving a pretty good results, at least for these three models, XComposer, MiniCPM, and GPT-4o, giving some non-trivial result on camera's view, let's just take a closer look from the camera's perspective. So to this end, we create another split of the benchmark, as we call it ball split, which aims at avoid the confounding factors introduced by the object intrinsic frames as well as the textures of the objects. So in this split, we only have balls, because balls have a unified view from any perspective. And we synthesize this image part of the split by moving the figure, basically red ball in this case, around the ground, which is the blue ball in this case. And each of the spatial relation just defines the canonical direction, which we denote it as theta equals 0 degree. For example, if we just talk about in front of, the canonical direction of in front of would be this direction. And all the theta would, for any kind of direction, for example, this, it will be basically quantifying the theta, the angle theta will be basically quantifying how much the direction of interest is deviating from the canonical direction of defined by some textual symbols. And for another example, if we are caring about the relation to the right of, the canonical direction is this. And if we are interested in this direction, then we define a theta here. This theta just quantifies how much this direction of interest is deviating from the canonical right-hand side relation. And we create for each relation, we create 36 possible theta values or 36 possible different image setups, just listed like here, and taking a step of 10 degree for each angle. And we also account for multiple colors and sizes that to mitigate the potential shortcut effect. All right, so the protocol is, again, just input the image and a corresponding textual caption into the model. And the textual caption will be looking like this. So is the red ball, which is the figure, relation the blue ball, which is the ground? And the relation, again, we consider 4 canonical relations, like to the left of, to the right of, in front of, and behind. Each of them could be inserted into the caption. And we just do a Carson product of all the generated captions and all the possible generated images. And again, we use the soft accuracy, and actually in this case, it's not accuracy, it's soft probability that the model assigned yes, comparing to the sum of the probability mass between yes and no. And we plot the soft probability of yes against theta. So here, I now argue cosine theta would be serving as an intuitive reference for the soft probability. So basically, if you imagine if the theta is 0, you should be expecting the model like be definitely positive. This is the relation, and cosine theta is just giving you 1. And you imagine if the theta is 180 degree, your model should be ideally just put 0 probability to yes and 1 probability to no. And this cosine theta is also giving you a reference that gives no. But by no means cosine similarity should be the ground truth of the model. All right, let's look at a few example results. For a bad model, the results look like this. So this dashed red line is the cosine reference. And as we can see, there's no correspondence between the dashed red line reference and the model performance. You can just understand the solid black lines as the model performance. So it's just a randomly, I can't say there is any correlation between the black line and the red line at all. For a back model, instructor blip, in terms of spatial reasoning, of course, instructor blip is pretty powerful in many object recognition and captioning tasks. But for spatial relation, we just observe almost nothing in terms of the correlation. But here is the model, here is a good model. Here's the result in the good model, which is X-Composer, the best model from our previous slide. So as you can see, the behavior for the relation, for the lateral relations to the left of and to the right of is almost like a stacking function. Well, the threshold set by the stack function is probably not exactly as expected. We probably expected the stack function threshold to be around 90 degree and minus 90 degree, but it's pretty much mapping the stack function with some certain threshold without too much deviation. And for the sagittal directions in front of and behind, the model performance and the model prediction is pretty much well aligned with the cosine similarity. So basically the key takeaway here is a good model is in general capturing pretty good spatial relations, at least from the camera's perspective. But if we just have a closer look comparing the two sagittal relations, what kind of difference you can observe from these two curves?
Question again?
Yes.
What's the question again?
So what kind of difference you will be spotting between these curves, between these two curves? So I'm now claiming there are kind of an interesting point in one curve.
In front of is wider.
Yeah, in front of is wider. Yeah, that's one thing. But actually, I'm going to focus on here. So here is a job. So actually, the thing is, you are expecting if the model exactly matches with the canonical relation, it should be assigning 100% accuracy into the canonical relation of theta equals 0. But why is there a job for behind? Yes, exactly. So what is happening is let's just look, take a closer look here. So actually, this is a systematic job. So this relation is also observed for GPT-4o and other strong models. And the thing is, if we just retrieve the train and car example, again, none of the audience except me endorsing this caption, the tray is in front of the car. And actually the model is to some extent showing like if your tray is, or if your figure objects is exactly placed in the behind. So actually the endorsement of behind is not that large comparing to the ones around angle 0. All right, actually, it's interesting, like the similar phenomena have been observed in human behavioral data as well. The 0 degree canonical behind, which is in the reflection relative frame adopted by most people, could be in front of in the translation relative frame adopted by me, and also many other non-English native speakers. So the job actually reflects the vision language model's capacity in adopting different frames. I mean, this is not a definite claim, but this is a hypothesis. Like the job is not a bug, is a feature and is an encouraging feature. And actually, more interestingly, there exists an asymmetry between in front of and behind. So if we consider these 4 captions, from the reflection relative frame, the tray is behind the car and the car is in front of the tray. So both of them are okay. And the tray is in front of the car is okay to me and many other people who adopt the translation relative frame. But actually, the car is behind the tray for this image is never okay to anyone, or at least much, much less okay to anyone, including myself. So the last one is actually least liked by humans, not liked as much as the third one, comparing to the component within the same reference frame. So that is to say, the job of this curve for the relation of in front of is much milder than that of behind. So we are actually pretty much excited to find this, as this kind of asymmetry is never supported by any psycholinguistic literature right now. And this result of this last caption, least liked by humans, are actually produced by our recent human behavioral results. And furthermore, we test some cross-lingual frame of reference adoption capability of language models. So some recent work, as I just mentioned, Bender et al. Just released some results showing that Chinese, German, and Japanese native speakers are more likely to adopt the translation relative frame of reference than English native speakers. So namely, the tray is in front of the car for this image. And actually, also, there are some conventional linguistic results. For example, Hill in 1982 shows that Hausa native speakers tend to adopt the translation relative frames more than the reflection relative one. And also Clark in 1973 released the result of Tamil native speakers generally adopt the rotation relative frame more than English native speakers. So rotation relative frame is basically, you can imagine there is another person sitting with you face to face, and you are more being sympathetic to adopt that person's relative frame instead of yourselves. And the quick question so here for analyzing vision language model is, are we able to observe similar preference in multilingual vision language models? For example, GPT-4o, it is claimed to be multilingual, and does the different conventions of adopting reference frames also exist in the multilingual vision language model? So to this end, we tested on 109 languages, where darker means, in this map is a little bit funny, darker means more favoring the reflection relative frame. But the thing is, I would just say this is basically a negative result. We didn't find any evidence for preference towards any other frames. So this figure is about the intrinsic frame, which is mostly adopted by a lot of American native indigenous languages, but the same thing also happens for other reflection relative frames. So that is to say, the conventional frame adopted by most English and Spanish native speakers, and also many other European language speakers, are dominant in term, even if the language is presented in another script. So the conjecture here is this may be because of the dominance of English in the training data. And actually, even if you are translating the captions into some other languages, this kind of convention in adopting reference frames is not transferring correspondingly. And a complementary view for spatial reasoning, recently done in collaboration with my student, Mike Agazi, we basically find, so for some of the spatial reasoning relations, the poor performance is probably not from the perspective taking capability, but also from data scarcity in terms of training vision language models. That is to say, VLMs don't see sufficient training examples for many of the spatial relations. And to quantify this, it's actually top 17% of the VSR spatial relations account for more than 90% MS COCO training examples. So actually, we have some free lunch. The proposed solution here is quite straightforward. After observing this kind of data imbalance between the spatial relations, we can just use some existing more detailed data to synthesize some spatial QA pairs and use the synthesized pairs to further fine-tune the language models or vision language models. So here's a quick example. So on the left-hand side is an existing QA data set, it's an existing image captioning data example, like the front view of a small gray elephant figurine on the left, and in the middle and on the right, and side by side, all of them are basically describing some spatial relations. But fine tuning directly on these is never working because these captions are so long and it's really kind of distracting. But we are trying to encouraging the model to recognize more kind of clean data by converting this long descriptions of the entire image into a list of QA pairs that involve spatial relations. And this conversion is done by directly inputting this caption or the detailed caption into a large language model to ask it to generate the QA pairs. And the results show it's pretty much reliable and we according to our spot checking. And the fine-tuning results is pretty encouraging. We compare to random baseline and human performance, which is pretty high actually, and GPT-4o, which is the state of the art at the time we conducted this research. And we fine-tuned the Q12 vision language model as the most powerful vision language model that has open weights. And actually, the key takeaway here is we are able to obtain much better spatial reasoning result with slightly or even no trade-off in terms of the performance on other tasks. So this is kind of a free lunch obtained by fine-tuning. But it actually, so even more encouraging, we are able to achieve like comparable result with just a 2 billion parameters with GPT-4o, and even better result with 7 billion parameters comparing to GPT-4o on spatial reasoning tasks. But actually, I still need to note there is still a huge gap between human performance and vision language performance, which needs further investigation. Maybe reference frame or perspective taking could be one of the promising directions here. All right, this concludes my first part of the talk. I'll pause here for any questions. Yes.
Can you explain why Chinese speakers are comfortable saying trees?
It's really hard to explain why. So that's my basic feeling. So this is just my own feeling. I'm not representing all the Chinese native speakers. What I'm looking at that is to basically imagining me, the tree, and the car is in the same space. It's not I'm looking at an image or a photo. So I just imagine
Does it
that.
depend on where you are in the space?
Yes, exactly.
Would you be sitting in the car?
No, I don't imagine I'm sitting in the car. I'm just imagining I and the car, and I'm an observer in the same space, and I'm observing the car and the tree.
Are you at the far side of the tree?
No, I'm just
What are you looking at?
looking into the image and imagining that is. So basically imagining I'm a robot and the image is actually the built-in camera of the robot. And so if that's captured, if the image is captured as a built-in image from a built-in camera of the robot, you'll basically just think from the robot's perspective, is indeed the case that tree is in front of the car.
So like I would say that the screen is in front of you.
Yeah, and actually from Sheila's perspective, if you take a picture and
I mean, let's say the car is looking at the.
I'm looking at you, looking at the screen,
I
yeah.
see. So yeah, I see. So it's like if the car were looking at the tree, you'd say the tree is on.
yes.
Turn.
Yeah, actually, I'm not doing this transition, but basically just imagining we are in the same space. Yes.
So I'm wondering what is the goal of this to train these things to have better spatial reasoning, or is the goal of this to expose the inherent ambiguities in linguistics through, what's being processed through language models?
Perfect question. I'll be discussing it at the end of the talk, but my point or quick takeaway here is we need to specify our goal. So in this work, our goal is to use the linguistic insights to analyze the vision language models and not intentionally use the vision language models or require them must be the human cognitive model.
I guess if the goal were just to do better spatial reasoning, then all of these things are ambiguous.
Yes.
And so you just assign coordinates, train it to assign coordinates to everything, and then compute some quantities that are frame invariant.
Yes, that is the perspective when we conducted that work. Yeah, but if that occasionally benefits the study of linguistics or cognitive science, that's great. Yes.
How do these results change if you were to use like a reasoning model?
Did you mean the visual reasoning model, for example, like having a chain of thought
Yeah.
stuff? We haven't tested that, but it would be interesting to look at this. I guess it's kind of nuanced in terms of the difference, and it's really hard to like require the model to put your perspective into some specific language speakers, or this requires pretty much prior knowledge about the world. Yeah, I'm not sure if the reasoning model could resolve all the tasks.
And so there's also research showing that, you know, when you have a vision language model, most of the outputs are like dominated by the language portion, and sometimes it doesn't even look at what's in the image. So is that like a failing of CLIP and the way that we build these things, or is it a failing of the encoder for the image? Just curious to.
This is an interesting question. Like, we identify the result of CLIP is basically just a say yes for everything. And probably it's not necessarily not looking at the image, but just a fail to look at the image properly for this types of question.
So I hate to believe it. If the car were pointing in the tree,
Yeah.
I would certainly say that, yeah.
Yeah, definitely that's the case. Yes,
But you would say that no matter which way they go.
yes, exactly. Yeah. This is also endorsed by some human behavioral data.
Yeah, it's interesting, as I was sitting here, I was thinking like, I'm to Raul's left, so. But I'm also to your left, but you guys are on either side of me, so it's because you're facing forward.
Yes. All right. I saw there's a question from Zoom. So what do you think are the reasons of the behind model outputting? Yes. I guess I have just answered this question. Yeah. All right. So I'll quickly going through the second part of this talk, which is we adopted possible word semantics and model logic to explain text-only language model behaviors. And the part of the recent literature we are particularly targeting in is the recent result by Helagonen et al. Basically, they show for some language model prompting or tasks, if you just design the prompt, which are mostly semantically similar or sharing the same semantics, the larger the perplexity, the poorer the performance, or the larger the probability, the better the performance. So perplexity is kind of in an inverse order of probability. So this is not surprising. And this kind of result is also endorsed by McCoy et al., Tom McCoy et al. Basically, they show the language models is kind of performing better on the common tests than the rare tests. So there, I'm just showing an example for both linear calculation, linear function calculation. The above is considered as more common than the below because the above is the way we convert Celsius degrees to Fahrenheit, and the below is just a banal linear relation calculation. And the GPT-4 model they found is basically just performing very well on the first task, but not the second with exactly the same format. So this is not surprising because language models are trained in a probability framework, and the more common tasks should be considered as kind of more in-domain training example comparing to the less common ones. And our question here is actually, yes, we agree that the perspective of probability explains things, but besides random noises, is probability or perplexity everything about accuracy? Is that everything about language model performance? So actually the quick answer in our recent work shows no, it's not the case. Logical forms, at least as one complementary factor, add some more explainability to the model performance. So in this work, we just say propositional and modal logic just gives us a pretty good framework to synthesize material for testing this rigorously. And we synthesize the kind of synthetic natural language within this template. So we start with the logical forms, like defined like here, basically logical sequence and policies, and translating them into templates and add some interpretation of each of the propositional variables shown above, and finally resulting in some experimental material to prompt the language models. So in this work, we consider both logic sequence and policies listed here. So basically it's an enumeration of hypothetical and disjunctive syllogisms. And basically, we are just asking the model, like, is it true that phi, or is it, so given the first condition, is it true, it is true that phi, and or it is true that psi, and second condition, like, it isn't true that psi is basically denying some of the disjunctive part, and then it must be true, like, that is phi. That is psi. And the key idea here is to following the formal logic systems, and we derive some experimental test material for analyzing the language model performance. And we also add the consideration of modalities, basically the box and diamonds. So the box you can just understand as must be happening, this propositional variable must be happening, and diamonds means this propositional variable may be happening. So actually, this just results in a pretty comprehensive data set, or by enumerating all the logical forms and the modal operators, and correspondingly the must and may operators will be translated into it is certain that and it is possible that to generate the prompt material for language models. And for the contents, we are actually considering some real-world scenarios to create some main experimental material to make sure these are in-domain data for the language models. And we manually selected some possible interpretations to minimize the content effect. So by content effect, I mean some prior rote knowledge that might be dragging you away, or dragging the language model away from correctly reasoning from a logical perspective, since here we are mostly caring about the pure logic reasoning capability of language models. So here's an example of dragging away by content effect. So if the first condition is, if Freda is giving a talk, then Freda is reading a book. And the second one is, Freda is giving a talk. And now my question is Freda reading a book? So based on pure logical reasoning, the answer is an absolute yes. But the thing is, you're seeing me, Freda is not reading a book. So you will be having some more tendency to answer no if affected by rote knowledge. And in the dataset creation, we just pay special attention to mitigate this and focus on the pure logical reasoning perspective. So to analyze the models, we fit a mixed effect model, which is a generalized linear model in terms of analyzing which part of the predictor or components is mattering more for the final predicted variable, which is soft accuracy. So the fixed effects can be understood as the linear coefficients in linear regression, and the random effects can be understood as the individual specific effects. So for the fixed effects, we basically consider the likelihood ratio test to support the inclusion of all the fixed effect predictors. So by the likelihood ratio test, we just figure out after removing any of these three predictors, the performance of prediction will be dropping. And for random effects, the inclusion of these two random effects, the constant and perplexity, are as follows. So basically, each language model might be having some systematically different performance. That's why we're including a random effect for each of the language models. So that is to say, for each of the language model, it has an individual Gaussian noise where the average is taking somewhere not necessarily to be zero, which is which is represented by the constant 1 listed here. And the perplexity means basically because we are using each language model's own perplexity as the predictor, so they might be systematically different in assigning higher or lower perplexity or probability to the material. So we also add a random effect per language model effect into this mixed effect model. So let's just look at the result. For the fixed effect modality and argument forms. So for modality, as we can see, the comparison of this segment and any other baseline is meaningless. So this is basically the estimated marginal mean. But we are interested in comparing these different estimations. So this figure just shows the model is more willing to say yes under the possibility modality may, and less willing to say yes under the necessity modality must. So this is kind of straightforward, like whenever you see something, is that a must? It's very likely in the real world it's not. So, but this kind of rote knowledge is really affecting the language model's logical reasoning capability. So technically, we are focusing on, again, we are focusing on pure logical reasoning capability. This shouldn't be something that affects the result. So actually, in line with Dentella et al., language models are more likely to respond yes under the possibility modality and no under the necessity modality. So Dentella et al. Basically says language model are more willing to answer yes no matter what your questions are. But actually, this result, just a complement their result, is basically showing language model are more willing to say yes under certain types of questions. And if we compare different categories of logical argument forms, we can see a clear tendency in terms of language models performing better on models ponens, which is quite straightforward in terms of the logical flow. In contrast to models tolerance is kind of less straightforward to people. And the result on argument forms just resonate with traditional result reported by Watson in 1968. And models tolerance is indeed harder for humans. And actually the related results on language models are also reported by Huang and Orgaf. Huang is actually from here, it's Sheldon Huang. He's not here sitting in the audience, but generally they also reported language models are struggling with models tolerance. Models tolerance. And the results on mixed effect of perplexity generally shows some encouraging results, which is basically the adds on random effects and fixed effect. And as we can see, the adding on between these two are all significantly lower than 0. So that is to say, the higher perplexity, the lower soft accuracy. So this line of result just resonate and cross-validates with the results I introduced initially by Gonan et al. And McCoy et al. And next, the constant random effect per language model. So intuitively, this constant effect should be quite well correlated with the general overall performance of language models in terms of the hard accuracy or even the overall soft accuracy. So that is to say, if this constant is larger for this specific language model, that is to say you are adding a free lunch into this specific language model's soft accuracy. And if it's lower, then it should be kind of adding some negative effect to the soft accuracy overall. So at the right-hand side, we are just showing the model soft accuracy ranking shown in the parentheses is generally showing a similar trend to the constant random effects, although they are not perfectly aligned because there are also random effects of each language model added to perplexity factor. Yes. Yeah, and in terms of accuracy distribution, so here is kind of more straightforward illustration, like language models, perplexity is not everything. So at the left-hand side, I apologize, it's not super clear for these dots. So there are dots for must as well. So left and middle basically just shows among the distributions with similar perplexity, there are clearly different performance better explained by modality and argument forms. And also the right-hand side shows there are significantly different perplexity. So here and around here, actually. But the performance is actually similar. If we just synthesize some material with nonsensical words, and actually the language models are performing logical reasoning pretty well, showing that they are acquiring some capability, even if on the data they are not being trained on. All right, I'll be concluding my talk with discussions on some thoughts. So first one is about synthetic data. So all of the work included in this talk is based on synthetic data. And I definitely acknowledge and agree with the perspective that synthetic data is not the whole world. This doesn't represent an important portion of the real world. And also the success on synthetic data does not necessarily imply success on the real data or real application. And also there are more kind of issues or problems introduced by training on synthetic data, such as model collapse, etc. But I wanted to argue from another perspective that actually synthetic data provides a clean test bed for analysis purposes, and we are able to just understand the model or system better in terms of the kind of clearly defined factors. And even if the success of synthetic data doesn't mean too much, the failure on synthetic data really means something. So failure on synthetic data really raises caveats in real-world applications. You probably don't want to deploy a system that even fails on some easy synthetic data. And finally, some thoughts on recently generative AI and sent to the question. So here, basically, I wanted to generative AI has pretty much exciting potentials, but what is our goal of building generative AI? Is that building a better, powerful human assistance? I'm actually not a big fan of building a powerful AI for no purpose, like only kind of building a kind of intelligence. I'm kind of more pragmatic, like we are either building AIs for assisting humans to be better, or we are building a better human cognitive models to understand humans better. So these two goals might be different in terms of research questions. So what questions are you asking about, or what kind of technical improvement you would like to work on? And also benchmarking protocols. For the first one, you probably want to build some ground truth evaluation benchmark and just trade the best, nice performance on the evaluation benchmark as the progress. And on the second goal, you probably need to collect more human data on specific tasks and compare model and human performance there. And also the desired training data availability is also sometimes different. So for the first one, I can't see any reason like less data is kind of sufficiently helpful. But actually along the second direction, human language acquisition is clearly done with a limited amount of data. You probably wanna, if you would like to make a claim on human cognitive models, you probably wanna kind of limit your training data availability to some extent. But actually, both of the directions require better understanding and interpretability. Along the first direction, you won't be hiring an assistant that you don't understand very well. Otherwise, it will be creating some math for you, and it doesn't really kind of take the responsibility for creating the math. And along the second direction, actually, using the language models or use generative AI as human language models is actually just for human behavior interpretability and understanding. So I envision that the better understanding and interpretability of generative AI are important in terms of both directions. And actually, both of them require personalized and pragmatic understanding of humans. So to build a better human assistant, you probably need to better understand human communication intention, and to build a better human cognitive model is certainly the one of the key requirements for computational psycholinguistics or psycholinguistics overall. So I wanted to conclude my talk that we're in an era where interdisciplinary insights are more valuable than ever. And I really value those kind of interdisciplinary collaboration. And I hope this talk just give you a spot how I and my collaborators use the linguistic insights to analyze the generative AI models. And yeah, thanks everyone for coming, and I'm happy to take any questions.
Any questions from the audience?
So you don't want to build powerful AI models just because it's cool?
I mean, yes, but but I
That
guess,
doesn't get you grants.
yes. But beyond the pure curiosity, I guess the application, I mean, the cognitive science line is also some pure curiosity.
So you started your talk by talking about, transformers as being very distinct from any of the linguistically motivated neural net architectures. So from what you found and what you presented in the talk, what are aspects of transformers that you think, be changed or modified to better capture some of these nuances?
I guess most of the current work is mostly focusing on behavioral data analysis. So I'm not exactly sure what exact architectural wise improvement could we make to transformers. So one thing we could think about is possibly a perspective taking module from both of the line of work, or having a theory of mind module. So clearly the transformers are not doing a perfect job in terms of recognizing other perspectives like theory of mind. And I'm not sure if having more data or basically some improvement on training framework, or just add some specific module to account for this capability is the correct solution. Maybe both and maybe neither. We'll see.
You mentioned interpretability. What do you think of making neural nets or transformers more interpretable, building in linguistic or spatial knowledge into their structure? Like having a neuron that represents anger. Yeah, is guaranteed.
Yeah. I guess from a kind of I'm kind of trained in a neural network era, and I'm definitely more favoring the end-to-end learning, and so I'm kind of interested in the task without any prior knowledge or with kind of human available prior knowledge, what kind of model we could build on top of this. So we don't know whether humans have a kind of perspective or angle neuron in our mind. But the thing is, if we don't have that, can we still have the transformers learning this? So again, this just goes back to the point, what is our goal for building AI? If it's for a general task solution, and it's not necessarily limited to the real space, building an angle could improve the performance on spatial reasoning, but maybe in the future, if we are thinking about the AI performance in some hypothetical world, I'm not sure if that's helpful or just inherently limiting the AI's performance.
What about, say, convolution translation? Does that mean you don't figure it out? That's a property of physical space.
I'm not sure if I'm favoring or against this, but I guess whatever model architecture that enables the successful processing of this data and enables some generalization and some scientific insights beyond what the model behaves like will be sufficiently interesting to me. So, but to some extent, I do think convolutional neural network is having some reasonable biases.
Just to play devil's advocate, for mice, we literally do know that they have location neurons and they've done experiments on it. So some aspect of that is actually built into biology. Whether it's gonna be helpful here, who knows, but.
So there's another question, Jackie.
Just the last.
All right. So what is your thoughts on the cognitive architecture like SOAR? Do you think those modules are necessary components? I'm not exactly sure what SOAR architecture was. Is that the state-of-the-art, the video generation model? Yeah, okay. Yeah, I'm sorry, I don't have a clear memory of retrieving what SOAR is.
All right, I think we can email Freda if we have any additional questions. So just want to say thank you again for joining
Thank you.
us for this lecture, and thank you to all of you for joining us here in person. So let's give another round of applause.